Okay, so welcome to this next video in which we are discussing the P2Y receptors. Okay, right. So we've now discussed all the different alpha, all the different beta, and all the different gamma subunits of heterotrimeric G proteins. Okay, so we're looking at these P2Y receptors, which are all G protein coupled receptors, and which, when activated by the binding of their ligands, are going to start interacting with heterotrimeric G proteins. Okay, so I now want to discuss the G protein cycle, which is the cycle by which heterotrimeric G proteins are activated by G protein coupled receptors. Okay, so let's start with activation then. Okay. So what's going to happen is the ligand is going to come and bind to our G protein coupled receptor, and the G protein coupled receptor is then going to change conformation so that it can interact with the heterotrimeric G protein. Okay, so let's draw the step before that has happened, okay, just so that we have that fresh in our heads, okay. So here is our G protein coupled receptor, and it's some P2Y receptor, let's say, at the moment. Okay, and then we've got our heterotrimeric G protein that's currently in the off state over here, which means that the alpha subunit is in the off state. It has guanosine diphosphate bound to it rather than guanosine triphosphate. Okay, so let's extend the membrane a little bit. And then we know that when the alpha subunit is in the off state, it will associate with the beta-gamma complex, consisting of a beta subunit and a gamma subunit, which is also attached to the phospholipid bilayer, like so. Okay, so let's add a bit of colour on here. So we'll have the alpha subunit once again in red here. Okay, we'll then have the beta subunit in blue. Okay, and the gamma subunit finally in green. Okay, so here's the beta subunit in blue, and then finally the gamma subunit in green. Okay, right. So what's now going to happen is our ligand, whatever it may be, is going to come and bind to our P2Y receptor. And remember, the P2Y receptors are a dopsin family G protein coupled receptor. So the ligand will bind to it within the transmembrane domains, basically. Okay, and now what will happen is the G protein coupled receptor, which has bound its ligand, is going to change conformation. Specifically, you're going to get a change in conformation in these free intracellular loops, so that the intracellular loops can now bind to the alpha subunit of a heterotrimeric G protein. Okay, so let's show this happening now. And I should say that different G protein coupled receptors, once they've bound their ligand, will want to bind to different alpha subunits of heterotrimeric G proteins. So let me draw this first, and then I'll expand on that point a little bit more in a moment. Okay, so what I'm firstly going to do is I'm going to spin the G protein coupled receptor around 180 degrees, okay? So that's just artistic license. All I've done is turned it 180 degrees. That's just to make the picture easier to draw, because I don't want the carboxylic acid terminus getting in the way of me showing this alpha subunit coming in and binding here. Okay? So what's happened now is the intracellular loops have changed in conformation, and they've now made available a binding site for the alpha subunit of our heterotrimeric G protein here. Now the alpha subunit will still have its lipid moiety attaching it into the phospholipid bilayer. Okay, so let's colour in the alpha subunit in red here. Okay, like so. And very importantly, is that the alpha subunit is in the off state. Now, the reason it's important that the alpha subunit is in the off state is that when it's in the off state, it will have a beta-gamma complex bound to it. And if the alpha subunit does not have a beta-gamma complex bound to it, it cannot bind to the G protein coupled receptor. Okay, so although the beta-gamma complex over here doesn't actually bind itself directly to the G protein coupled receptor, it is essential that the beta-gamma complex is bound to the alpha subunit in order for the alpha subunit to bind to the intracellular aspect of the G protein coupled receptor. Okay, and in order to have the beta-gamma complex bound to it, the alpha subunit needs to be in the off state. i.e. it needs guanosine diphosphate bound here rather than guanosine triphosphate. Okay, so now let's talk about the fact that different G protein coupled receptors will bind to different alpha subunits. Okay, so depending on the G protein coupled receptor, it will show preference for binding to different alpha subunits, and therefore will only bind heterotrimeric G proteins which have certain alpha subunits. So let's discuss this for the 8 different types of P2Y receptor. Okay, so we'll start with P2Y1. So which alpha subunits does P2Y1 like? Well, basically it likes heterotrimeric G proteins of the GQ/11 type. Now remember what this means. This means it's going to bind to heterotrimeric G proteins where the alpha subunit is within that family of G alpha Q/11. And remember I told you that this family, they all pretty much do the same thing, so they're not easily distinguishable basically. Okay, so P2Y1 likes to bind to heterotrimeric G proteins which have one of these 4 alpha subunits here. And to show that shorthand, we just put GQ/11 to say heterotrimeric G proteins where the alpha subunit is within this family of G alpha Q/11. Okay, right. Now let's talk about the P2Y2 receptor. Okay, this also likes to interact with GQ/11 heterotrimeric G proteins. Okay, so it likes to bind to heterotrimeric G proteins where the alpha subunit is within this family of G alpha Q/11. Now the same is true for P2Y4 and P2Y6. Okay, so these two are also coupled to GQ/11 heterotrimeric G proteins, meaning that when they are activated by their respective ligands, they will bind to heterotrimeric G proteins which have an alpha subunit within the G alpha Q/11 family of alpha subunits. Okay, right. Now let's talk about the rest of the P2Y receptors. So we have P2Y11, which I'm going to leave for a moment, and then we'll talk about P2Y12, P2Y13, and P2Y14. Okay, so P2Y12, 13, and 14, these are all coupled to GI heterotrimeric G proteins. Okay, and remember this means that the alpha subunit of the heterotrimeric G protein will be either G alpha I1 or G alpha I2 or G alpha I3. So one of the 3 basically. Okay, so they show affinity for heterotrimeric G proteins where the alpha subunit is either G alpha I1, G alpha I2 or G alpha I3. Finally, P2Y11, this shows affinity for both GQ/11 heterotrimeric G proteins and also GI. Okay, so these are the least fussy. They will bind to heterotrimeric G proteins where the alpha subunit is either in the G alpha Q/11 family or is either G alpha I1, G alpha I2 or G alpha I3. Okay, so those are the different heterotrimeric G proteins which the different P2Y receptors will interact with. Okay, right, so now let's complete our discussion of the G protein cycle. Okay, so the G protein coupled receptors bound to the heterotrimeric G protein, like so, and to do that it required the beta gamma subunit to be bound to the alpha subunit. So specifically, the intracellular loops will bind to the alpha subunit of the heterotrimeric G protein, but the beta gamma subunits are necessary in order for that binding to occur. Okay, and what's going to happen is when the alpha subunit binds to the intracellular loops like so, what will happen is it will allow the alpha subunit to release its guanosine diphosphate that is bound to it, and instead it will bind a molecule of GTP from the cytoplasm. Now, when the alpha subunit binds GTP, what happens is it goes into the on state, and in the on state, it no longer binds to the beta gamma complex. Okay, so the beta-gamma complex goes off, basically. It cleaves off the alpha subunit. Now, once the alpha subunit has lost the beta-gamma complex, it can't bind to the to the G protein coupled receptor anymore. Okay, remember the beta-gamma complex being bound to the alpha subunit was essential for the alpha subunit to be able to interact with these intracellular loops of the G protein coupled receptor. I'm sorry, I keep wanting to call the G protein coupled receptor the heterotrimeric G protein. Okay, so basically, once the beta-gamma complex is left, because the alpha subunit is now in the on state, the alpha subunit will lose its ability to bind to the G protein coupled receptor, and therefore it too will go off on its own little adventure. So let's draw this here. We'll try and squeeze it all in, and then we can draw a nice cycle. Okay, so we've got our alpha subunit here going off on its own little adventure now. Okay, and it has GTP bound to it, like so. And then we've also got the beta-gamma complex over here, which is also going off on its own now. Okay, now the alpha GTP subunit over here will go and bind to some target within the membrane. Okay, like so. And it will either be a target that is an integral membrane protein, or at the very least is attached to the inner leaflet of the phospholipid bilayer, just like the subunits of the heterotrimeric G protein are. Okay, so let's call this target 1. Now, it's important to remember that the beta-gamma complexes also have targets. Okay, so we'll call this target 2. So both the alpha subunit over here and the beta-gamma complex will go and interact with targets, basically. Okay, and they will trigger downstream pathways. So for instance, alpha subunits within the alpha S family go and activate adenylyl cyclases. Alpha I's family alpha subunits, so alpha I1, alpha I2, alpha I3, those all go off and inhibit adenylyl cyclases. G alpha O has similar properties along with other members of that family. The transducins we've discussed, they're different. Okay, G alpha Q/11 will go and activate phospholipase C enzymes of the beta type, and G alpha 12/13 go and interact with pathways involved in cytoskeletal remodeling. Okay, now what will happen is not only when the alpha subunit with the GTP bound to it binds to target 1 does it affect the behavior of target 1, but also this binding interaction also affects the behavior of the alpha subunit, because the alpha subunit is actually an enzyme. Okay, it's actually a GTPase enzyme. It's capable of hydrolyzing GTP into GDP and an inorganic phosphate. And when it binds to its target, what will happen is the target will activate the alpha subunit's GTPase activity, okay, and it will now hydrolyze the GTP it has bound to it back to GDP, and therefore it will turn itself off effectively. Now, when the alpha subunit hydrolyzes that GTP to GDP and turns itself off, it can no longer bind to target 1, okay, because only the on alpha subunit can bind to target 1. So as soon as the alpha subunit turns itself off, it cleaves off target 1, and it then goes back crying to the beta-gamma complex over here, snatches the beta-gamma complex off target 2, and will return to the inactive heterotrimeric G protein here, like so. Okay, and that's the G protein cycle. That's why it's called a cycle. It's the cycle of going from this inactive heterotrimeric state to the state where it's being activated by the G protein coupled receptor, to the activated state where we're interacting with targets, and then back to the inactive state. Okay, right. So, to summarize then, we have these 8 different forms of P2Y receptors which are activated by both uracil nucleotides and also adenine nucleotides. Okay, and when they are activated, they are all G protein coupled receptors and will interact with certain heterotrimeric G proteins as listed here, and those heterotrimeric G proteins will then go and have that archetypal signaling pathway. So GQ/11 will go off and activate phospholipase C enzymes of the beta family, okay, and the GIs will go off and inhibit adenylyl cyclases. Okay, so that now concludes our discussion of the P2Y receptors.